Okay, and that we should memorize some of these pKs because it tells us something about their overall reactivity on how acidic they were. And we could backtrack through, and based on some conversations in the tutoring center, I think there's some weaknesses with understanding equilibrium and reversibility of chemical reactions. So we need to kind of talk about that a little bit. If we go through and look at a chemical reaction, okay, in this particular case, we have reactants and products. You'll note we have a box where we would typically see what? An arrow, a reaction arrow. And what we've seen in Chem 130 is that universally they show that as an arrow. Okay. What you should have also seen in Chem 130 is that that is not true. Okay. Our reactions are not unidirectional. Our reactions go both directions. Okay. But drawing it this way is also misleading. Why is it also misleading? That would suggest that it is going equally forward and backward. And that's also not necessarily true. Some reactions, whoops, I wanted an eraser, go forward a whole lot more than they go backwards. Some reactions go backwards a whole lot more than they go forwards. Okay? Why is it important for us to recognize that interplay or that balance? Okay, well, if we're going to try and make something, what kind of reaction do we want? Do we want it to go forwards or backwards? Forwards. Okay? Because if we're making something, if I want to make a building, I don't want to put all the wood and nail together and be like, okay, here we go, and now start taking apart all the wood and nails to even smaller pieces. That's not what I want to do. I want the wood and nails to come together to build a larger structure. Okay? I want it to be one directional. Okay? Even then, when we build our houses, do we want our houses to just fall apart? No, theoretically, we want them to last forever. Okay? As the owners of said houses, we would want them to last forever. The builders, of course, don't want that because they want to make money by having to build more buildings. Okay? Or to fix the old broken buildings. Okay? That's a bit cynical, but close enough. Okay? When we look at chemical reactions from an organic point of view, we just want to go forwards, okay? Typically. Okay? We can leverage reactions that go backwards and forwards because of a change in our materials. So if we go through and look at this particular reaction, this molecule and this molecule are of particular interest to us. Why? How are they different from this one and this one? So we could go through and look at the change in what's happening with them, okay, which is powerful. Okay, we could say that this first one acts as an acid because when we compare it to the black on the other side, it has lost a hydrogen. So it does act as an acid. And if it acts as an acid, what is it reacting with? Cool, it's reacting with a base. Okay? All of that is true, but that's not the question I asked. Why do I care about the structures in the black, but not the structures, I guess now in our colored, but I'll make them all blue, in our blue? What class is this? It's not just chemistry. And what is organic chemistry the study of?
Organic.
What is organic? Carbons and hydrogens. And if we look at those black boxes, those have carbons and hydrogens. So those are of particular focus and importance to me. Okay? If we look at those structures, we could go through and evaluate their difference in chemistry. We could note that the other one would be our conjugate base as it reverses the reaction. This one would be our conjugate acid. Okay? All well and good, not super necessary for us. Okay, so why do I care? Why do I care about this acid-base system? What changes as I go from my acid on my reactant side to my conjugate base on the product side?
You lose a hydrogen.
Cool. That's the definition of an acid. What else changes?
Your base, or your acid that turns into a base, becomes negative.
Ooh, it becomes ionic. Okay. Why is that important to me?
Stability.
We'll come back to stability.
Interaction.
Ooh, interactions. The intermolecular forces change. If I take a look at that product, I'm looking at ionic, I would call them ionic, but we could call them electrostatic forces. And if we look at the forces for our starting material, do we have that same force?
No.
No. We have primarily hydrogen bonding. So we have a difference in our intermolecular forces. What does that difference do for us? Well, if we have different forces, that means how it interacts with another substance would also be different. And so what I can do is leverage that difference in forces to allow me to change the properties of one molecule into the properties of something else. Okay? In the lab, we use this to separate that compound on the left away from other things, because we can change its intermolecular forces from hydrogen bonding to ionic, and the ionic electrostatic are almost universally soluble in water. Whereas hydrogen bonding sometimes is, sometimes isn't. Okay? Because it now changes phases, I can separate. Okay? It's really hard to separate a liquid from a liquid. So what do we do in the lab to separate the liquid from the liquid? We didn't do extraction to separate a liquid from a liquid. We did distillation. Well, what is distillation? What did I do with the liquids?
Heat.
Why does that help?
Evaporates.
Getting the right idea. It took my liquid and it turned one of them into
A gas.
a gas. Because the gas and the liquid have different properties, I can now separate them. Right? So we leverage different intermolecular forces to allow us to do different manipulations to separate and purify things in lab. Okay? Here, what we're introducing is now not a passive process, but an active process. I am chemically altering the structure. Okay? And by chemically altering, it allows me to separate. Right? If we're thinking about a separation technique, we also want to be able to reverse that chemical alteration. And this is why acid-base chemistry is so nice, because guess what acid-base chemistry is? Reversible. Okay? I can change the direction of the reaction by adding stronger or weaker acids or adding stronger or weaker bases to change my reaction dynamics around. So they're very easy to reverse. They don't change the overall structure. The carbon skeleton stays constant, right? But the only thing that changes is the presence of that hydrogen or not, and that is lovely. Right? So I can go backwards and forwards. So how would I be able to predict whether it goes backwards or forwards? Okay? Well, that has to do with that box in the middle. Okay? If I did this, which way do you think the reaction goes?
That way.
To the products. If I did this, which way does the reaction go?
Reactants.
To the reactants. Okay? How do I know what arrow I should put in there?
You want a more stable one.
I want the most stable products to come out. Okay? And how we evaluate stability is something that is challenging to nuance. That's the reactivity kind of schedule that I gave you within the lecture videos, and we'll come back to that kind of ranking system because it helps us to think through whether a reaction does or does not react. Okay? That's evaluating structures. I would argue we should be in the business of evaluating structures. We should not be in the business of memorizing random facts. Okay? But we can also do this by memorizing random facts. Okay? Those random facts come from looking at a chemical experiment and testing. That looks at the K, the equilibrium constant, which is really saying what's happening within that box. Does it go to reactants or does it go to products? Or is it someplace in between? That's the K value. That K value is calculated by taking the concentration of our products and dividing it by the concentration of reactants. Well, how do we get to the concentrations? We'd have to run an experiment. Okay? We literally have to go in and do an experiment to figure those out. Okay? That's why this process is generally not the greatest process to be doing, because every single substance we have has a new K expression, which means a new calculation to run. Okay? But what we can go through and do is we can rely on other people having run those experiments to give us some information about those K values. Okay? So we could do it for this particular thing. The other thing we've discovered is that we can create this K value by looking at other K values. I can look at the K value for this just acting as an acid. On its own, the H plus and its conjugate base over the acid, and I can look at that K value. I can also go through and I can look at the K value for this species, which would then be our H plus, its conjugate base, over the acid. And I can compare their K values to each other to predict which way the reaction goes. That involves a lot of math and calculations. Okay? But ultimately what those tell us is which way that particular species wants to react. Okay? So if I look at this black K value and I get a large number, what does that mean?
It's not very, the pH is,
It's products. So, we can do pH. Probably don't want to do pH. pH is a calculation based off of H plus. Do I have the H plus? No. I have a relationship that allows me to solve for the H plus if I have all these other values. So if I add all those values and the K, which we said we were trying to figure out, I could then rearrange, solve for H plus, then I could solve for the pH. Do I want to really do all that? No. If I have a large K value, what does that mean? Well, how do I calculate K? Products over reactants. So if I have a large K value, what does that mean about this particular reaction? I have lots of H plus and lots of conjugate base, which means this species wants to donate H plus. Because a large K value means I have a higher concentration of the reactant or the products over my reactants. Okay, what if I had a small K value?
not a lot of reactants.
I have a very small amount of reactants. So a small number over a larger number. It gives me, again, a small K value. Okay? So I can look at the size of that K value, my black K value, and I can compare that to the size of my red K value. Because the red K value is ultimately looking at the exact same thing. They're both producing H plus. Okay? So what happens if I have a larger black value than I have a red value?
More products.
If I have a larger K value, that means the conjugate base is in a larger concentration than this one's conjugate, which was here. So what does that mean? More products. A larger black K value means more products. And if I get more products, what does that mean about my reaction arrow?
It's going to favor the products.
It favors the products. Okay. What is large?
Whole numbers.
10 to the positive number. How many people like powers of 10? Okay. That's now a challenging thing to manipulate. What is a small K value?
Negative power.
10 to the negative power. We may not have liked positive powers of 10. You certainly are going to have a hell of a hard time with negative powers of 10. Okay? Everything hits the fan, it becomes a mess. So scientists went through and said, I don't like dealing with powers of 10 also, so I'm going to create a mathematical system that gets rid of the power of 10. What is the mathematical system that gets rid of powers of 10? It's the log. Okay? And so what we end up doing is converting the k value by taking the negative log, mathematical mumbo-jumbo, of that numerical value that's a huge power of 10, and this usually gives me a number between 0 and 50. Okay? What does that now translate to? Well, number one, that gives me, loses kind of powers of 10, and I can deal with numbers 0 through 50 relatively well. Okay? So let's say the k value, this black one comes in with a k value of 3, and this one comes in with a k value of, or sorry, pKa value now, because we're doing the negative log. What does that mean for us? We said a large k value for the black meant we favored products. What does the pKa value mean? And if you're like, I'm really confused by pKa's and negative logs and all that, yeah, that's okay. Okay, you will be. And you're like, do I have to calculate all? No. What you have to be able to do is to interpret what those numbers mean. The smaller the pK value, the larger the k value. It's like, what? Welcome to negative log. Okay, that's what it does. So if I have a small pKa, that means I get lots of products. Whoosh. A large pKa value means I don't get as many products. And because this red one is now looking at the reverse reaction, what happens? Which way should my arrow go? If I have a pKa of 3, and we can simplify this all now, get rid of all that junk, and I just have a pK of 3 versus a pK of 10. Which way does my reaction go? A small pK meant a large K. And a large K meant more products. Damn. It inverts all over hell and gone. Okay? And that's because we're dealing with this concept of equilibrium. And again, that is a challenging concept to address. Okay? It is one that should have been addressed in Chem 130. Whether it's stuck or not, and I can almost guarantee it did not stick, okay, is a separate issue. When we talk about it, what we're trying to get at is that we can look at a chemical reaction and we can now start to predict where the reaction goes. Okay? And if you're like, what's that thing in the upper right? Don't worry about it. There's some calculation stuff that we don't want to stress about. Okay? What we want to be able to do is look at a reaction and be able to predict something about it. In that prediction, we can fall back on experimental results. But to fall back on experimental results, I must have those experimental results. Which means, what do I have to do? I have to memorize them. Do you want to memorize those? Okay. And if your answer is no, that's okay. But then that means you have to shift your focus to be able to interpret overall structures, okay, and stability of structures. What do I mean by that? We can go back and look at this reaction and say, which way do I think it should go? So I don't care about any of this. I just want to look, well, technically that bottom part is kind of useful. Which way do I think this reaction should go? Should it go to making more products or should it go to making more reactants? Okay, products. What makes you think it should go to making products? Because of the pKa values. So you memorize the pKa values? Okay. What were the pKa values for this molecule? I'll accept 3. Usually I would say it's about 4.2. Actually, that's technically acetic acid. I think you're right. I think 3 is a little bit better. What's the pKa for this? Okay. The numbers that I wrote down were arbitrary numbers. They weren't numbers that matched with this. What I was trying to write down is numbers that matched with your conversation about which direction you wanted it to go. Okay? I know, that's nasty, isn't it? What is the pKa of that molecule? Cool, damn, we don't know it. And if we don't know it, how do we know which direction it goes? We have to be able to interpret something about the structures. So, look at your structures. Okay. All reactions do the same thing that humans do. We progress to levels of stability. So when you come into this classroom, you had to walk, right? Because it's kind of inappropriate to butt scoot along, the center walkway, right? Okay, dogs get away with that, and even then we laugh at dogs for doing that. Okay, so you have to walk. But then you come in here, and then what happens? You sat down. Why'd you sit down? Why aren't you standing? I'm standing. It's a lower energy state. So when we progress through, you go to lower energy states. There are things that can cause you to go up or down in energy, okay? But our natural flow is to go down in energy. All chemical reactions do the same thing. How do we get them to go up? We have to put in chemicals that are higher in energy that force them to go up. Or we have to add enough heat to force them to go up. That's how it works. So again, we can look at it and say, well, which one of those states do I think is more stable? Do I expect the reactants to be more stable, or do I expect the products to be more stable? Why?
Because when I think product, I just think end result, which means, I want to be more
Right.
stable.
Except that you're now making the assumption that this is a reaction arrow like that, right? What if the reaction arrow was that?
I don't want the reactants to be more stable.
Okay? So your answer is changing based off of your perception that reactions should always go left to right. That perception, as we've now addressed, is wrong. You cannot use that perception. It is a flawed system. The only reason we talk about that, like chemistry like that in Gen Chem, is we're trying to keep it simple and say, let's just look at the simple examples. Sorry, reality hits hard. We have to be able to evaluate. Okay? In that system, which one of those is more stable? Have we talked about stability before? Yeah? What makes things more stable or less stable? Oh, that's a lovely answer. Charge. So, which side is more charged? Okay.
Or negatively charged, or
Just charged.
Oh, yeah.
The right side is more charged. Okay. I'm going to come back to you because, Crystal, I think you were like, but wait. What's your but wait?
Yeah, I think I answered too quick because I noticed I didn't see the negative charge on that side.
Okay, or the negatives and positives. Okay, I can accept that. Okay, overall charge has to be constant for a chemical reaction. But we can distribute the electrons differently within an individual molecule to create formal charges. Okay, so we're saying the product is more charged. Okay? Is charge a good thing or a bad thing? Is it stabilized to be charged? Said another way, imagine your current situation where you're at, but now we decide to add some charge to your current situation. Okay? And by charge, we can take a cattle prod and I just walk up and hit you with a cattle prod, right? That's charge. is that going to put you in a higher energy state or a lower energy state? Higher. So is charge a stabilizing feature? No. Charge is massively destabilizing. Systems will minimize charge. So what does that mean for us? Which way does the reaction go? Towards the reactants. If we'd memorized pKa's, 3 is ballpark, I think, right for benzoic acid. 4.2 is the one stuck in my head, but I think that's acetic acid. pKa for the other acid on the other side of the equation, negative 1.5. Okay. When we did the 3 to 10 example, we went to the 10 side because it was less likely to go forward. So our reaction went toward the larger number. Which number is larger, negative 1.5 or 3? 3, which means the reaction should go
to the right.
To the left, again, towards the larger number. So we can use pKa's to make these predictions. Okay? How does this translate out into other things that we could discuss? Well, other things we could look at is we could reference a reaction coordinate. Okay? The reaction coordinate says I'm moving from reactants to products. Okay? And I can look at the energy of my reactants. Well, they're all neutral, so I would expect the energy of my reactants to be about there. What would be the energy of my products? Well, they're charged. Because they're charged, what happens? They're higher in energy. So for my reaction to occur, I have to go up a hill. Is that going to be easy? No. Okay. Could I get it to happen? Yeah. Okay. And the extent and the amount that it happens is going to become the next question, which we're going to modify in this. When we run a chemical reaction, it's never just here's one spot and here's another and we just go straight lines. Okay? When we run a chemical reaction, okay, we have to go over an activation barrier. That is the activation barrier for the forward reaction. This is the activation barrier for the reverse, because I'm going from here up over this hill. As soon as I clear that hill, I can now make it over to the other side. Okay? That activation barrier changes the speed at which a chemical reaction happens. The smaller that activation barrier, the faster that reaction. What does that mean for us? If we look at our reaction, doing the reverse happens faster. What happened? That's exactly what we predicted. That's kind of neat. For the record, I've never done that before. Okay? The energy diagram allows us to interpret that. Okay? That's what's happening within our process. We can get this question of extent. So if we look at this energy diagram, let's say we move to a different reaction. Okay? Reactants, but okay? Would I expect a different balance of reactants and products now within this potential system? Why would it be different?
Because they're at similar energy levels.
Okay. They're at similar energy levels. Okay. With the products being higher in energy, they don't really want to form. It's hard to get to them. If I make them similar energy levels, there isn't a driving force for the reaction to happen. Okay. Or the forward or reverse to happen. So it will just kind of balance out and we'll get equal levels. We could also create a system where we get something like this. This energy diagram now suggests that I should get lots of products. Okay? Because the products are much more stable than the reactants. So I can use energy diagrams to interpret this. I can use the numerical values to where do the numerical values go? They go into drawing out the energy diagram, to actually quantifying it. Do you like numbers? No, thank you. I don't like numbers either. So we really don't want to deal with the quantification. We just want to know ballpark what's happening within it. Okay? Higher, lower, and that's it. Okay? So we can deal with that with pKa values, or we can use structures to make those interpretations. Okay? So let's try some structures. Sure. Okay, let's take a look at our carboxylic acid. I want to know what happens structurally to the carboxylic acid, which presumably would act as what? An acid, right? It's in the name, would suggest. Okay, so let's just take advantage of that. Let's just say it acts as an acid. What would be a good base to react with an acid? Okay. Can you name any good bases? Okay, and water can act as a base, but is it a good base? If I pour water on myself and I'm like, I'm melting. You're like, yeah, of course you do, Mike. You're a freaking witch. That's not how it works. Bicarbonate could work. We could use sodium bicarbonate. But sodium hydroxide is a more common one, so we could lean on sodium hydroxide. Okay? And now one of the things that we want to be able to do to predict a chemical reaction, there's a couple things. If we know acid and base, ta-da, we can now lean on that to come up with our chemical reaction. Okay? The other thing that we could go through and do is actually take advantage of figure out what I'm trying to do. Take advantage of what we know about the bond types within these. Do any of the bonds in either the acid or the base stand out to you as something potentially unique or different? Bonds. Kind of like what we've been doing this entire unit. Let's evaluate the bonds. Once we know the bonds, we can predict forces. Well, also with the bonds, we can predict intermolecular reactions. Hydrogen bonding is not a bond, it's a force. What are our bonds?
Or covalent ionic.
Cool. There's three types. Which of those three types do you see?
Polar.
Cool. Where do you see polar?
OH.
Cool. Where else do you see polar?
O.
There is no OO.
No. I know. I was testing you.
Okay, I appreciate the test.
You have carbon and hydrogen.
Is carbon and hydrogen a polar
No,
bond?
not polar. I'm just going through native bonds.
Okay, so you switched topics on me. That's fair.
Okay.
Okay, the carbon and hydrogen is going to generate
Is
what kind of
sodium and
bond?
Oxygen polar? No.
It's a weird question, unfortunately. Is it polar? Technically, is it a polar covalent bond? No. It's an ionic bond because sodium's a metal. That's an ionic bond. Okay. Oxygen to carbon is a polar covalent bond. Carbon double bond to oxygen is a polar covalent bond. How about carbon to carbon?
No.
That is non-polar covalent. How about carbon to hydrogen? Non-polar covalent. Technically, there's three of those. Okay. What forces are generated out of those? London dispersion. Pause. London dispersion is generated for which bond? Non-polar covalent. How strong of a force is London dispersion?
Not very.
Not very, which means is it likely to predict anything about our chemistry?
No.
No. So when we go through and look at this molecule, we have an immediate step that we can do. delete. I don't care about it because it's not going to be involved in the chemistry. Okay, continue.
Me?
Sure, anybody.
Your polars are gonna be dipole-dipole?
Your polars, dipole-dipole, or hydrogen bonding, depending on which one we look at. Okay.
Carbon to oxygen will be dipole-dipole for both of those. Oxygen and hydrogen will be hydrogen bonding.
Okay, so cool. Those are pretty strong forces, so maybe those are relevant ones for us to consider. Except what's the last one? Ionic.
Is it,
And what kind of force do we get from ionic? Is that a strong force?
Yes.
Yeah, that is the strongest force. And it is so strong because what do the electrons in that bond do? Opposite of that,
they steal?
they do not share. So when I see that ionic bond, what I should be seeing is a negatively charged oxygen and a positively charged sodium. I should then remember from my Gen Chem a special rule about sodium. Sodium is always a spectator ion. What does it mean to spectate?
Watch.
It watches the game. It's not relevant to me. Okay? So now I can go through and look at these and be like, well, what kind of chemical reaction should I predict will happen? Where should I start my focus?
Your OH.
Be a little bit more clear because there's two OHs.
So this oxygen.
Okay, as you're pointing, the red oxygen, the negatively charged
Negatively
oxygen,
charged oxygen.
should be where we start because it is the strongest force. Okay, what does that negatively charged oxygen need?
Hydrogen. Electrons.
Does it need electrons? How many electrons are around it?
No, but it wants it.
How many electrons are around our oxygen?
6.
Try again.
7, 8.
8. Octet rule. Okay, all the way back to the first unit, we have to use that content. Okay, can it get more electrons? No, because it would exceed its octet. It cannot get more electrons, so it is not going for electrons. It is negatively charged. What happens when I take a negative and bring it near more electrons, which also happen to be negative? They repel. So I do not want to bring that negative oxygen near more electrons. What do I want to bring it near? And I understand what you were saying with the hydrogen, but I want a little bit more clarity behind it. What do I want to bring that negative near?
A positive.
Ah, a positive. Okay. Where is there something positive in the other molecule?
The hydrogen.
I don't see it as positive. How are you seeing it as positive?
Because it has a bond to the oxygen.
Why does that make the hydrogen positive?
Because yeah, there's 2 there.
What do the electrons in that orange bond spend most of their time doing?
Hanging out on the oxygen.
Hanging out with the oxygen. Why?
Because it's more electronegative.
Yeah, that's why it's a polar covalent bond. Which means if those electrons are moving this way, it's actually, I don't like that orange arrow, I want a green arrow. What's happening to that hydrogen?
It's losing
It's losing electrons. And what charge did it start?
It starts positive.
Does it say positive?
No, it starts neutral.
It starts neutral. If it is losing electrons, what happens?
It's becoming positive.
It's becoming positive. We have to throw in the partial because it's not formally positive. What happens to the oxygen? Partially negative. Okay? So now where do I want my negative oxygen to go? I want it to find a positive atom. Where's there a positive atom? That hydrogen. So I can take those electrons and I can share them with the hydrogen. Okay? If I share those electrons with the hydrogen, what happens?
It becomes
I accept that. It makes a bond with the hydrogen. That's it. Okay? So I should show that new line. Okay? But didn't I have that orange bond to another oxygen? And if that was the case, if that was my product, what's the issue? What is the problem with my hydrogen in the middle?
Too many.
The octet is exceeded. Am I allowed to exceed octets on hydrogen? No. So what had to happen?
Had to break off.
It had to break a bond, either the green bond or the orange bond. I don't care about any of the other bonds because the octet being exceeded is on the carbon. Right? I could break the green bond on my new drawing, but I don't want to break the green bond because I just made that bond. Let's break the orange bond. Okay? And if we break that orange bond, we'd be adding a curved arrow, right? To show that the electrons move away from the exceeded octet. What did I draw right back at the beginning?
An arrow.
That exact arrow. Which means if I pay attention to the arrows that I drew, is that orange bond actually there in the product? Nope, it's not there. Okay. So have I now drawn it correctly?
No.
Why not?
The oxygen's missing some.
The oxygen's missing electrons.
Can I draw two?
Why do I want to draw 2 more dots on it? Couple answers. Oh, I just want to satisfy the octet. I can't just arbitrarily decide I'm going to satisfy the octet, so here's electrons. Okay, you're okay.
Well, because it took it from
Ah,
the
yes. That arrow meant the electrons in that bond are now sitting on that oxygen, which means the lone pair is indeed there. I can't just delete it. It did come from that arrow. What does this result in? New structures. I've run a chemical reaction. I broke a sigma bond. That's a chemical reaction. Okay. If I actually want to push this a little bit further, we said we could ignore the CH3. We can ignore it in the sense of it's not doing any chemical reaction. Okay. But if I go to shake someone's hand and we just focus on the shaking of hands, okay, what happens to the rest of my body during that process? Does it just disappear? No, it's still there. Which means when we go through to draw out our product, we need to make sure that that CH3 is still there. We can't just delete it. Okay? Is that now a good formal product? No. Why not? Unit 1. Octets are fine.
The oxygen needs to have 2 bonds.
The oxygen does not need to have 2 bonds. Like, oh, oxygen needs to have 2 bonds. Did you give me that issue when I drew out sodium hydroxide? No. So don't tell me oxygen needs 2 bonds. It does not need 2 bonds. What does it need?
Oh, it needs a charge.
It needs a formal charge. Again, unit 1. If you have those tools at your disposal, you don't have to be constantly thinking these things. It's already ingrained in your nature to be drawing those. That was the point of unit 1, to make this unit easier. Okay? We've now done a chemical reaction. That's this unit. That's pretty wicked and cool and neat. What kind of chemical reaction did we do? Acid-base. How do you know it's an acid-base reaction? You're like, you're an idiot, Mike. It says acid-base up there. Of course it's acid-base. Fair, I get it. Okay, why else? There we go. If we look at what changed through the course of the reaction, the location of a hydrogen changed place. We took this hydrogen that was connected to our organic structure, and we put that hydrogen on a different molecule. That's an acid-base reaction. It's a transfer of a hydrogen from one location to another. Okay? So yes, it says acid-base. Fantastic. I like that. I like even more that you're leaning on the definition of what an acid-base chemical reaction is. Okay? Now the next line. Should this reaction progress forwards? We drew the arrow going towards the product because what we were trying to do is predict what could happen. Not that it happens, but it could. How do I know that this reaction arrow is correct? Or should it instead perhaps be this way? Or should it just be a straight up equilibrium? How would I know? Cool. pKa's. That's a lovely answer. We could use pKa's for this. This slide conveniently says we should memorize pKa's, which means, of course, you did. Sorry, bus coming right at you. What's the pKa for our first acid? Okay, fair. What's the pKa for this acid?
15.7.
Okay, so if we have those pKa's memorized, we could drop in those pKa's. This one's 15.7. This one was 4-ish. Which way should our reaction go? Towards the larger number. It should go towards the products. Ta-da! There it is. How many of you memorized all of those pKa's? Okay, fudge. Okay, well, if you don't have the pKa's memorized, you can't use that. So how do we figure out whether the chemical reaction worked? How did we do it with the previous one? You remember the previous one? How did we go through and say that this reaction favored the reactants, not the products? We looked at the charge, okay? And we said the products were more charged than the reactants, and therefore we should favor the reactants. So let's go up and look at this chemical reaction that we've drawn above, and let's do the exact same thing. Let's find the charge. So is the first molecule charged? No, those are partial charges, but they're not formal charges. We're looking for formal charge. Oh, that is charged. I got a negative oxygen.
Yes.
Yes, I've got a negative oxygen.
Partial charges.
And partial charges. Okay, so if we go through and evaluate this based off of charge, okay, so cool, fine and dandy. Mike said that we could go through and do this. So the reactants have a negative oxygen. The products have a negative oxygen. Which one is more stable? Say that with gusto. They're the same. Because they are. But are the oxygens the same? No. So there is something different about those structures. Right? So what we now want to go through and do is, does the structure affect the stability of the negative charge? So I want to look at the rest of the molecule. So when I go through and look at the reactant side, I have a hydrogen. Does that hydrogen do anything to that negative? No. Okay. What about the other side? Could that do anything to the stability of that negative oxygen?
No, but the carbon can affect the carbon and the carbon can affect the oxygen.
Okay. Unit 1. What makes up the charge? The what? The extra electrons. So what's making up the charge is that lone pair of electrons. What can lone pairs of electrons do? Yeah, they can make bonds, but we're talking about the overall stability of this, so I don't quite accept bond, because we're looking at its character. We're not talking about a chemical reaction. What do you mean they can move? Don't never mind me. That's the answer.
Well, they can move like from bond to atom.
Oh, lone pair electrons have the ability to move from an atom to a bond. But if we did that, wouldn't we exceed the octet on that carbon?
Yes.
Yeah. Which means I can't do that. Except, what else could I do? What have I just done? What'd you say?
Resonance.
I just did resonance. What does that resonance do to the charge on that oxygen? It removes the charge. It neutralizes the charge, which means the charge is less charged. It's more neutral. So which is more stable? A neutral oxygen or a charged oxygen? Which way does the reaction go? Other way around. The reaction goes away from charge, which means the reaction progresses towards the products. To be able to do that, what did you have to be able to do almost on reflex?
Structures.
Yeah, you had to be able to do resonance. It's almost like we talked about that in Unit 1 because it is directly relevant to everything we do for the rest of the semester. Yes, that is exactly the truth. Right? All of that content comes back and back and back. You cannot forget it. Or you memorize everything. Okay? So when students go through in the past and have said, oh, organic chemistry is so much memorization, because they chose to memorize. You are welcome to choose to memorize everything. 100%. It will make me grumpy, but that's on me, not on you. You can memorize everything you want. The problem with memorization is a very subtle change in the structure can make you go from, oh, I totally get this, to what the hell is this? Okay? You remember that whole chirality thing? How happy you were with chirality? Oh, this is easy. And chair flips and all of those? All that was a bond rotation, and you went from, I don't know what this structure is anymore. Very subtle changes to structure wipe memorization from your ability. So memorizing things is not a good strategy. Okay? This is why people freak out and say OChem is all memorization, because they actively chose or passively chose to not learn the content. This is why we've spent so much time trying to address what these things are and how to manipulate them so that you don't have to memorize. Okay? Yes, that is insanely depressing. And you want to see how really insanely depressing it gets. If we push into the video that you were told to look at, right, we just talked about acids and bases, and you're like, oh my God, this is ridiculous. That's one of 5 overall reaction types. You're responsible for recognizing all of those reactions. And if you're having trouble memorizing just acid and base, throw in the other ones. Yep, it goes through hell real fast. Okay? Because you need to be able to apply the content forward. There are extra symbols that pop up within this. At this point, you don't really need to stress about those symbols, because those symbols can be anything. Anything at all. Okay? What you have to recognize is that they've changed locations. That's it. So if I look at the substitution reaction, hopefully the substitution reaction looks kind of familiar. What does the substitution reaction kind of look like? Kind of. I took this thing from over here, and where did I put it? On that molecule. You mean I transferred something from some place to another place? Right? Why should that sound familiar? It's acid-base. Okay? But it's not acid. Why is it not acid-base? Because the something is not hydrogen. Acid-base very particularly is referring about the transfer of a hydrogen, and that is the only thing that you can do. A sigma bond change from hydrogen in one location to a hydrogen in another location. That is it. Substitution is effectively doing the same thing. It gets a little bit more complicated, but it's effectively the same thing. I take a group and I change its location to another spot. Okay? But that thing that I'm moving is not hydrogen. Well, how many things are not hydrogen? A lot. So when we talk about just overall chemistries here, substitution is effectively the same pattern, but now we're talking about transferring a whole crap ton of different things. Okay? We could move to elimination. What's happening in elimination? What do you see changing when we look at these structures?
Break the bond, connect,
What bond did you break? I like that.
the double bond,
You broke a double bond.
no,
No, you
break on the net,
you broke the Lg bond to make a double bond. So if we look at the elimination reaction is going to make double bonds. Did substitution talk about double bonds? Nope. Okay. And what did we learn about double bonds? Is it good to reference things as double bonds? No. What are double bonds? They're a sigma and a pi. So when I go through and do this reaction, I'm not making a double bond. I'm making one bond. I'm making a pi bond. Okay? And yeah, I got to break the leaving group off. So I had to break the leaving group to make a pi bond. Is that all that changed? That was aggressive. You knew that right away. No, something else happened.
The electrons on base, should I be looking at that?
That's fair.
They turned into a sigma bond, a hydrogen sigma bond, I guess.
Cool. So when we run this reaction, this base somehow formed a bond to a hydrogen. Where'd that hydrogen come from?
silver,
What did I just draw on this structure?
The implied.
The implied hydrogens. There's that hydrogen. So when I did the elimination, yes, I broke the bond to the leaving group. I also broke a bond to a hydrogen. That's what allowed me to make the pi bond. That's all implied information. I wish somebody had told me about implied information, say in Unit 1, that we needed to watch out for it and make sure that we didn't forget about it. Okay. Addition. What happens in addition?
Make a pi bond,
Loss of a pi bond
forming two sigma.
and forming two new sigma bonds. Okay. The names, all these different colors in there, are clues to the context of what those things are acting as in the chemical reaction. Okay. We heard one reference that was probably the easiest reference. In green, it says solvent. Have we talked about solvents?
Yes.
Yeah. We had protic, we had polar, we had nonpolar. Are choosing solvents going to be relevant for any of a particular chemical reaction? Yes. In this class? No. Yay, one less thing. Okay. What else shows up that's colored that you might have a clue about? You took, oh my, wow. Really? That's where you went? You didn't go with like base. That maybe the base is going to act like. Oh, come on. What do bases act like?
they receive.
Bases. Bases act like bases. Okay? And if we go back to your reaction, you said it gained a hydrogen, right? Well, what do bases do? They gain hydrogens, which means the base acted like a base. So if we know the definition of bases, we can see that they're relevant for this elimination reaction. Are they relevant for substitution? No, why not?
Because there's not a base.
You didn't write base in that one. Yeah. Yeah, that's perfectly awesome. Okay? What you're trying to do is key in off of those terms and manipulate those terms in these particular scenarios that allow these chemical reactions to happen. So you have to be able to see these pieces. Okay? That is challenging. I 100% get that. Okay? We got Annie over here seeing elect and going electrophile. You're not wrong. Like, that was phenomenal. But, like, of all the ones to pick, that's probably the hardest. Elect being electrophile. What do electrophiles do? They accept electrons. They would take things from something else. What happens to the pi bond? It breaks. It breaks to make a sigma bond. Where do those electrons go? To forming the sigma bond with the electrophile. Okay? Because electrophiles want electrons. Well, what is a pi bond? A source of electrons. The electrons can go to the positive. So if I know those definitions, I can start to manipulate what those structures are doing and how they change their characteristics. Okay? What was nuke?
They want neutral.
It's not neutral. Oh, they want. You're giving me a definition. I get it. What's the name for it? What's the extended name for nuke?
Nucleophile.
A nucleophile. Nucleophiles seek out positives. If we go back to this bottom reaction, those electrons go to the electrophile. Right? If they go to the electrophile, really what we've said, is that those electrons somehow make that bond. So they're kind of shifting down to this carbon and then going up here. What happened to that carbon?
Charged.
Good, do better.
Became positive.
Why?
Because it lost electrons.
Lovely. If we consider how those electrons are moving, that carbon has now lost electrons. And if it lost electrons, it's now positive. It would need electrons. What thing could supply electrons? How about a nucleophile? Because what are nucleophiles doing? They love nuclei. And nuclei are positively charged. So what must the nucleophile have to be attracted to a positive? There it is. What does that mean? When I look at the product, I would expect my nucleophile to be connected there and my electrophile to be connected there. Wow. Why? Why don't I see the electrophile connected here? We're talking about how that pi bond moves around. Do we have anything that helps us to explain how pi bonds move around? Pirate's favorite letter. That's just a clue, by the way. It's not the answer.
It was like the scary thing. That was the acronym.
R. Do we know any words that begin with R that would have reference to a pi bond? Resonance. That pi bond can potentially move around. We could have those electrons move down here. If they did that, we'd form a negative charge here and a positive charge here. That would explain why the nucleophile electrophile aligned. Couldn't I have just as easily said the electrons go this way? What would that have produced? The negative charge there and then the nucleophile and electrophile should be in opposite locations. But I didn't draw that. Why not? Why is this a bad drawing? The red one also has charge. Which charge are you more confident in, positives or negatives? Negative? Okay. What would make a negative happy?
Giving the electrons.
Giving the electrons to something else. So if we look at these, we're talking about how either of them give electrons to something else, which means we don't have a comparison. What we have to decide is how is this negative in the blue different from the negative in the red? What's near the negative in the blue? Hydrogen, carbon, and carbon. What's near the negative in the red? What's the difference between carbon and hydrogen? The amount of electrons. The blue one has more electrons near the negative. Is that a good thing or a bad thing? What happens when I bring electrons near electrons? They repel, which means, is that a good thing? What does that mean? Blue thing doesn't happen. All I get is the red one. That's why when I run that reaction, I only get that result. What are we using to determine that? Basic atomic building blocks of where negatives and positives want to exist, near other electrons or not. That's the point. We're using those exact same fundamentals that we built up in Unit 1. And we now have to apply them. Guess what's going to happen in Unit 3?
Do equations.
You're now going to have to take everything from Unit 1 and Unit 2 and apply it to Unit 3. And guess what Unit 4 is?
1, 2, 3, 4.
I'll give you a little bit of a break. It's not 3. Unit 4 will be 1 and 2 and 4. 3 and 4 are kind of independent of each other. You're just looking at more reactions within those systems. Unit 3 is mostly going to be substitution elimination. Unit 4 is going to be our additions, and then some of the kind of crazier stuff at the back end of those. Okay? Within all of that, what we're trying to do is recognize the patterns of our chemical reactions. We're trying to balance out rankings. We want to be able to determine stabilities. And we talked about some of these things. We looked at resonance effects. That's a molecule effect to differentiate stability of charges. But we'll look at charges. We looked at charges to evaluate where a reaction went. That's number 1 on our list. So this sequence here is what you'll be using to decide whether something should go forward or should react or should not. It's all based off of looking at those atomic and then molecular effects. It's amazing how applicable those rule systems can become. Okay? This is where the ion stability comes in. It's the exact same principle. Okay? We just walked through that. Okay? And then where it's really going to push into, this now summarizes the entire rest of the semester. These are the fundamental building blocks on how we do all of our chemical reactions. Acid-base was one of them. It's a reaction where all of the bonds are making and breaking at the exact same time, known as simultaneous. Okay? We have SN2 as a type of mechanism. E2 is a type of mechanism. Do you need to know what SN and 2 stand for? Eventually, but not right now. What I want you to be able to do is to look at a mechanism and be like, that's SN2. That's it. That's E2. That's it. Acid-base? Yes, you need to predict. Right? That's our one reaction that we're looking at in this unit. And what we're going to start to do is now just look at reaction after reaction after reaction and practice those so that you can recognize what's happening. Once you can recognize what's happening, you can now start to build. And if you can't recognize what's happening, your alternative is rote memorization. Right? Right now, these mechanisms you should memorize. Right? How should you know what they are? That's the point of the video that goes through and gives you multiple examples of each and asks you and shows you what's happening at each of those stages. Right? That's the whole point all the way through. If you have questions about that video, that is fine. We can get to those questions and we can look at specifics. My plan for all of next week is really going to be to do this. What mechanism happens here? Oh, it's ugly, This becomes the problem. We see so many different pieces and we have to focus very carefully on what's going on. Let's push on elimination. What does elimination mean?
Break the bond and
Make a pi bond. That's the big piece. I start with a pi bond and I end with a pi bond. Did I make a pi bond? No. So is it elimination? No. Okay. What changed? Right? We are officially done, but I'll walk through this real quickly on just what changed. What can we do? That's resonance. I don't care about resonance. I just want to know the bare minimums of what changed. Okay? Did the carbon-oxygen double bond change? No. Okay. Did something change here? Yeah, what changed?
Is doping one hydrogen?
This hydrogen has appeared to have disappeared. It is no longer found over here. Which means this species must have acted like
Acids.
an acid. Which would then mean it would have needed to react with a base. Is sodium hydroxide accepting that hydrogen? Yeah? What chemical reaction is it?
Acid brings.
It's acid base. You mean that step with all these crazy weird structures and all that newfangled stuff going on with it is just an acid base reaction that you've studied for admittedly probably only like a semester and a half? Yes. Yes, it is. Very easy to lose track and all the other stuff moving around. Stop it. Focus where the chemistry is happening, and that is it. Tons of practice. And with that, we will